Hi everyone, welcome to General Astronomy. Today we are going to start, or continue I should say, talking about the sky and get into motion and different types of motion in our sky. So by the end of this week, you'll be able to classify and compare stars based on apparent brightness, label directions on the celestial sphere, determine the location and vantage point on Earth based on photos or diagrams of star trails, explain circumpolar stars, and also describe the positions in the past and also in the future of the North Celestial Pole and our North Star. So to start, let's think again about the celestial sphere. So remember, this is an imaginary sphere outside of Earth that holds all of the celestial bodies. So it's essentially if we took the sky all around Earth and pretended it was one sphere, it looks to be constant and like it is rotating around us. Now we know that that is apparent motion. The apparent motion from east to west of the celestial sphere is apparent because we know it is Earth that's rotating. So Earth rotates around its pole. It rotates to the east, which is why it appears our celestial sphere is rising in the east, setting in the west. So it is Earth that's rotating, not the actual stars and our sky, but when we think about the sky, we think about this celestial sphere. So as if all of the celestial bodies, stars, planets, the sun, the moon, were all projected on this sphere around Earth. And we remember that that sphere is broken up into 88 constellations. So here is a GIF or a video showing what's actually happening, where we have this celestial sphere that has all of our stars on it, and the Earth is rotating itself. So it makes the sky look like it is moving from the east to the west throughout the day and night. And remember that it's not just the sun, not just the moon, but the moon, the sun, the stars, everything moving together. Or everything appearing to move together, I should say. So when we think about stars, when you look up at the sky, there's a large range in what we see. So one large thing we think about with stars is the brightness. So ancient astronomers, when we first started looking at stars, came up with a magnitude scale to discuss and compare the brightness of stars. So the scale went from 1 to 6. 1 was the brightest star that you could see. 6 were the dimmest stars that you could see. So this scale went from 1 to 6. 1, the brightest stars, and then the larger the number, the fainter the star. So 6 were the very faintest stars, 1 was the very brightest. Now, more modern astronomers have taken that scale and extended it, because with all of our technology at this point, we can see many more stars, and we know a lot more about the stars that we can see than the ancient astronomers did. So we stuck with that 1 to 6 scale and just extended it in both directions. So from 1 to 6, we have that original scale, 6 being the limit of the naked eye. So 6 being the limit of what you can see unaided with your eye at night. As it turns out, there are a few things that are actually brighter than what ancient astronomers called a 1. So Sirius is the brightest star in our sky. That's actually about a -1, -2. Venus, the planet, quite bright at almost a -4. We have our full moon and our sun, very, very bright. So those are so bright that they are past the 1 on the ancient astronomers' scale, so they're actually negative numbers. Now, very, very dim objects are so dim that they are past the naked eye limit, so they are actually higher on the scale than a 6. So the higher the number in apparent magnitude, the fainter the star appears to us on Earth. The brighter the object, the more negative the more negative the apparent magnitude will be. So we call this apparent magnitude because it's how bright are these objects from our vantage point on Earth. So the thing that this doesn't consider is the distance of the object from Earth. So this is just looking at how bright are these objects when we are here standing on Earth? So that is apparent magnitude. So we use a lowercase m, v, for apparent magnitude. So how bright from Earth's point of view, and it's just the observed energy flux from the star. So just what we see here on Earth. Now, if you want to talk about the actual brightness of the star, we have to think about the distance from Earth. Because if there's a very, very, very bright star, putting out a lot of energy, but it's incredibly far away from Earth, it might not appear very bright to us. So its apparent brightness might be quite low. Whereas if we have a rather dim star that's very close to Earth, that might appear very, very bright to us. So the apparent magnitude is just how we are viewing the brightness of these stars. Now, in order to compare the actual brightness, we look at what we call absolute magnitude. So you'll see a capital MV for absolute magnitude, whereas apparent magnitude is the lowercase m. So this is where we are thinking about how bright is this star from 32 light years away from the star. So this is consistent. 32 light years away from every star, how bright is it? So we're measuring the actual brightness of the object, the actual brightness of the star, of the planet. So this is the real luminosity of the star. How much energy is it outputting? What is the real brightness? Not thinking about how bright is it from us, but actually, how bright is it? How much energy is it outputting? What is the energy flux? So we standardize by saying, thinking from 32 light years away, how bright would that star appear? So here's a comparison. So this is Sirius, the brightest star in our sky. Here on the left is showing the apparent magnitude of this asterism. So the brightest star in our sky is called Sirius. It is right here. Now, if we look at the absolute magnitude of these stars, I should explain. The circles, the dots here are sized by brightness. So apparent magnitudes, here we have Sirius as the brightest. These medium dots are less bright, and then the teeny tiny dots are even less bright than that. Now, if we look at the absolute magnitudes here on the right, we see that the star Sirius isn't actually that bright of a star. It isn't actually outputting that much energy, that much light. Most of the other stars around it are actually brighter. There is a higher luminosity of all these other stars around it. However, from our viewpoint, Sirius is the brightest star that we can see in the sky. So from that, we can assume Sirius must be closer to Earth than these other brighter stars. Otherwise, we would see these as brighter. So since we see these brighter stars actually as dimmer, that must mean they are further away from us. So here is another apparent magnitude map of the same asterism and constellation. So here, this is the Big Dipper is in this constellation. So here is the brightest star in our sky. So again, the dots are in size in terms of magnitude. So you'll see that a 0 is about this size. Here is a 1. There are many magnitude 6 stars here that are right at the edge of the naked eye limit. But you'll see Sirius is so large that it's actually on the negatives because it is the brightest star that we can see from Earth. So with apparent magnitude, we are able to calculate and compare objects to each other, compare their apparent magnitudes. So the difference in 5 levels of magnitude mean that an object is 100 times brighter. So a magnitude 1 star is 100 times brighter than a magnitude 6 star would be. So if we break that up to see what's the difference between just one level, it is a difference of about 2.5. So a magnitude 1 star is 2.512 times brighter than a magnitude 2 star. So the key is to remember that a difference of 5 magnitudes is 100 times brighter. So a difference of 1 magnitude is about 2.5 times brighter. So if you were to look at, well, what's the difference of 2 magnitudes? So say a magnitude 1 to a magnitude 3, you would calculate 2.512 times 2.512, which means that the magnitude 1 star is about 6.3 times brighter than that magnitude 3 star. So here are some magnitudes of common limits that we think about. So the sun, the brightest thing that we can see, the full moon, Venus when it's at its brightest, Sirius, which is our brightest star. Then we have the naked eye limit in the city. So in an urban sky is really more like a 3. So we can't see anything greater than 3. If you were out in away from light pollution in a really dark sky, you could see up to a magnitude 6. So if we wanted to calculate, we have star A and star B. Star A is a 2nd magnitude star. Star B is a 6th magnitude star. So we can see that there's a difference of 4 magnitudes between A and B. So how would we calculate the difference in brightness between star A and star B? So remember that the difference in one level of magnitude is 2.5 times brighter, 2.512. So in order to calculate what's the difference of 4 magnitudes, we would do 2.512 times 2.512 times 2.512 times 2.512, which equals 39.81. So star A is almost 40 times brighter than our star B. So what we did here was we did the 2.512 times itself 4 times, because it's the difference of 4 magnitudes between this 2nd magnitude star and 6th magnitude star. So star A is almost 40 times brighter than star B. So let's think now about the sun versus our full moon. So here we have the apparent magnitudes of our sun at a negative 26.74. The apparent magnitude of the full moon is a negative 12.74. So if we want to say how much brighter is the sun than the moon, we need to find the difference. So the difference in apparent magnitude, is 14. So the difference between these two values is 14. So there's 14 levels of apparent magnitude between these two objects. So what you could do is 2.512 times 2.512 times 2.5, 14 times, which would take a really long time on a calculator to type that in, and I would most definitely make an error. Or you can think about this 14 in simpler terms. So remember I said the key to remember is that 5 levels of magnitude equals a 100 times brightness difference. So a level of 5 magnitudes difference means that the stars are one star is 100 times brighter than the other. So what you can do is split this 14 into smaller, more easy to manage groups. So what I like to do is remember, 5 is going to be 100 times, so I can split this 14 into groups of 5. So I can say 5 plus 5 plus 4. So I know the 5 and the 5 are going to be 100 times, so all I have to do is calculate the 4, which means I only have to type in 2.512 4 times. So what you can do is say 100 times brighter for the first 5 times 100 times brighter for the second 5, times 39.81, which we calculated back here when we looked at this difference of 4. So now we can multiply that 100 times 39.81, and we find that the sun is 398,100 times brighter than the full moon. So the sun's pretty bright. This doesn't give you proof not to stare at it with your eyes. We'll get to that later in class. So instead of typing out that 2.512 times 2.512 so many times, you can always break this difference in magnitude up by remembering each difference of 5 in magnitude is going to be 100 times brighter. So that's just a little shortcut that might make any calculation like this a little bit simpler. So here we have some famous stars in our sky that you should start to become familiar with. So Sirius, which we've talked about, is this brightest star in our sky. So it's in the northern sky. It's the brightest star that we can see. And then you'll also notice there are two stars listed here in the Orion constellation, Betelgeuse and Rigel. So you'll notice Betelgeuse is the brightest star in this constellation, Orionis. So it is called Alpha Orionis. Remember that we talked about the naming of stars. So some stars have these older names from the ancient astronomers, but they will all also have a more modern name, which is a Greek letter and then the name of the constellation. And the Greek letter starts at alpha and then beta, and it goes through the alphabet based on brightness within that constellation. So you see these two are in the same constellation. It is both the brightest and the second brightest star that are listed here. They are in Orion. And then here I point all of these out. We also have Polaris, which is our North Star. Here it is. So Polaris here is in the Little Dipper. And we have Polaris in the Little Dipper, and we have the Big Dipper here shown as well. So we will get a little bit more into our North Star in the next lecture video.